Okay, so the problem we are going to try to solve today is binary tree maximum path sum. So looks like the question says that we are given a non-empty binary tree and we need to find the maximum path sum. Now what is a path sum? The path sum is basically um, sum of a bunch of nodes, a sequence of nodes from a node to any node in the tree along the parent-child connections. So basically any path, like you just pick any two nodes, if you can go from one node to the other node, which you should be able to do in a tree, um, the path you traverse, the shortest path you traverse to get from the first node to the second node is going to be the um, path sum. So I think trivially this problem should just be um, the maximum path sum in the left subtree or the right subtree, or um, the maximum path sum going down in the left subtree along with the value at the root, and the maximum value going down the right subtree. So what do I mean when I say going down? I mean starting from minus 10, you shouldn't consider a path that goes 15, 27. It should only be a path that goes 20, 15, or 27, because obviously if you include this whole path, then you can't really add anything to it at this point. So either minus 10, 27 or minus 10, 20, 15. Okay. So to me, that suggests we have at least one other function. So let's say we call this a straight path, like a path from 20 to 7, or a path from 20 to 15 is a straight path, and a path from 7 to 20 to 15 is just any path. So we would basically want to return max path sum in root.left. Let's assume this is a list, so max path sum root.right, or basically straight path, or max straight path in root.right plus max straight path in root.left plus root.back. And if this was a list, we would need to return basically the maximum of all these values. In Java, that would be mat.max, and we need to individually get these. I can't create a list on the fly in Java, so let's do it this way. So now what's left is we need to implement the rest of max path sum, because it's a recursive function clearly, but we have not defined a base case yet, so it'll just recurse infinitely, and we also need to define max straight path. I believe the solution should work. It may not be optimal because we may be repeatedly computing max straight paths. For example, if we call max straight path on 20, depending on how we compute it, we may be repeatedly computing it for like the tree that starts at 7, if there was a tree starting at 7, and so on. But let's see what we can do. I think it may pass without needing to optimize that. So first things first, if root is null, then we return 0, because there is no maximum path if there is no path. That ensures that these cases will get handled recursively. If root is not null, then and root dot left and right are null, then the first two, um, the first things here, this and this should both return 0, and then we need to ensure that this is implemented correctly. So let's get to that and make it a private function, since one outside this class needs to be calling it, and it takes a node. Let's name this node instead, just so we don't confuse ourselves by using root where we are not supposed to. So if the node is null, then we should just return 0, because again, if there is no path, then the maximum sum of a straight path is going to be 0. However, if there is a straight path, how do we compute it? So it's going to be basically the maximum of root dot left dot val, or let's say root dot val, plus this can actually come outside, because you'd be adding root dot val to both the node's left subtree or the node's right subtree. Actually not to the node's left subtree, but the max straight path arising from the node's left subtree, and max straight path arising from the node's right subtree. Okay, let's just do a brief check of if this works. So let's say we start with this input 1 2 3. So now node is pointing to 1, root is pointing to 1, and we say mat.max of max path some root dot left. So let's start there. We recurse, and now root is 2, and then this would return 0, this would return 0, and now we need to go into max straight path. So max straight path would, on root dot right, would basically return 0, this would return 0, and root dot val is 2. So max path sum at 2 is 2. Okay, that's as we expect. And math.max path sum root dot right. So now we need to compute it for 3, and this would go the same as 2, and so this would return 3. And if not, we basically get max straight path of root dot right. So now max straight path of 3, and that would be 3 plus the maximum of max straight path node dot left, which is 0, or node dot right, which is 0. So this would return 3. Similarly, this would return 2, and this would return 1. So that would give us 6. Let's also do a test with this one. I'm just going to put it in the input. I think it should work, since it should basically go into this recursive subcase, and within that subcase we have root as 20, and 20 root dot left would be 15, max path sum of 15 or 7, or max path sum of root dot left 15 would return 15, this would return 7, max straight path of root dot right 7 would return 7 plus null null, and max straight path of root dot left would return 15. So 7 plus 15, 22 plus 20. I think it should work. It should give us 42. Oh, it looks like I did exactly what I said I should. I ended up confusing myself, but it's good now. We know that we're not accidentally using root. Hopefully we haven't mixed it up in our heads. Okay, that worked. Wondering why this is considered a hard problem. I guess it's because of this condition. If we return 0 and So let's say we have a tree with only negative nodes. We would fail because we return 0. So one thing we can do, um, we can return null and add a bunch of null checks. Trying to see if there is a better way to do this. We could use integer.min value, but then that would fail if one of the values of the nodes is integer.min value. I guess we have to basically check for null. I don't really like about Java. So we can't really return null because we need to return an integer data type. Let me see if integer.min value would work. I guess that should work because at most it can be integer.min value. For example, if we had a node that was basically the lowest value an integer could take, that is the maximum possible. So we can't go any lower than that, is what I mean. So this should be fine. This would be valid. Let's test it out. I'm just going to submit it. Wonder if it'll get a time limit exceeded. No, but it failed. Okay. So looks like we should also be see if we can just return root.val. That's probably why it was a hard question. A lot of corner cases we can miss out on. And here too. So sorry. Here basically be it's compared with 0. It's the same as not adding anything. I think that should work. Wondering if there's another edge case where there are two negative values. Okay. Yes, that's all. Okay, so this should return 2. Wonder if I can. Okay, let me visualize this tree. Okay, so the left child. So it should return the maximum of root.val. Okay. So let's see, we start at 1. Root is 1. Root.val is 1. That's clearly not the maximum. Max straight path. Root.right. Oh, the issue is okay, I get it. So rather than doing it that way, let's basically say you don't have to take a node on the right. You just stick with that we have. Um, what about a case where we start off with a really negative note, but then and slightly less negative? Okay, that works too because of these checks, right? I think this should work now. Okay, that was easier than expected. I suspect that it's a hard problem because of the counter conditions. You see these wrong answers. They're they're not good. Like these should have been thought of while coding it. Let's see if we can make this quicker. That and we'll basically say the map, the computed value in the map is not null. We just return that value. Else we basically put that value in the map. And we can return this. Okay, we check to see if it succeeds. To be an integer object. If it's not present in the map, this will return null. Okay, and let's submit it and let's see if we get an improvement in the runtime. Yep, a huge improvement. So this is basically reduce the time complexity to O of n, where n is the number of nodes. We can look at some solutions. And another one. It looks like I'm having some difficulty pulling the solutions up. Let's just look at the previous one. Okay, so as you can see here, they've used the min value and they're finding the maximum path down the left. So where we call it a straight path, they're using the terminology path down, and they compare the maximum of, they basically use a global variable to hold the maximum value, and then get the maximum of the left subtree and the right one, and they either use the actual value or just use 0, because you don't have to include the left subtree in the path. You can just start the path from the node and go down the right subtree, or vice versa, or just use the node value. The way they do that is by including the zero here, and then also they basically return. Um, yep, that's actually much cleaner. So they return the maximum of the left or the right and no dot value. So this will give you the maximum straight path or the maximum path down because you're picking only one of the two and adding it to the node value. Um, yeah, picking one of the two or not picking either. So that's what the zero does. It's pretty neat. Okay, thanks for watching.